Welcome to this video on fine structure of hydrogen spectrum. In this video, I will explain what is the meaning of fine structure and derive expressions for it. In the early days of quantum mechanics, Bohr's atom model was the only one that described the discrete nature of hydrogen spectrum. He was able to explain the various series in the spectrum, but people soon realized that the energy levels are not single lines, but each accompanied by a set of closely spaced lines. This is called fine structure. There are two mechanisms. There are two mechanisms that contribute to fine structure. The first one is the relativistic effect. Non-relativistic Schrodinger's equation is inconsistent with the special relativity. There are corrections to the equation. Second contribution coming from is called the spin-orbit coupling. Electron spin interacts with the magnetic field of the proton, which depends on its orbital angular momentum. This is called spin-orbit coupling. I will explain this in this lecture. First, First, we start with the relativistic effects. The kinetic energy operator in the Hamiltonian needs to be changed to incorporate special relativity. Classically, Hamiltonian is of the form T plus V, that T is the kinetic energy and V is the potential energy. In the non-relativistic case, T is P square by 2m, but in the special relativistic case, T is given by the total energy minus the rest mass energy. For a given momentum p, the total energy is square root of p square c square plus m square c to the power 4. Hence, t is square root of p square c square plus m square c power 4 minus mc square. T is equal to mc square times square root of 1 plus p over mc square minus 1. We can expand the square root in the power series, and we get we keep the second term, and the first term is the usual non-relativistic expression for the kinetic energy as used in the Schrodinger equation. The second one is the perturbation, that is, second one is taken as a perturbation due to special relativity. And then to proceed to quantum mechanics, we replace the coordinates with the respective operators. X going to x, p going to p hat, momentum operator. We take HR prime to be a perturbation to the non-relativistic Hamiltonian. According to perturbation theory, corrections due to a relativistic effect is the expectation value of the perturbing Hamiltonian in the unperturbed state. U1R is equal to h prime r, expectation value of h prime r, is equal to that depends on the expectation value of the operator p to the power 4. P to the power 4 expectation value can be written in terms of the direct product of states with p square psi operating on it. Now the Schrodinger's equation is given by p square psi is equal to 2m times c minus v times phi. This means U1R is equal to 1 over 2mc square times the expectation value p minus v whole square. E is a number because it is an eigenvalue, but V is an operator, so we need to take the expectation value of the operator. Substituting in the above equation, the expression for V, we get E1R is equal to minus 1 over 2mc square times En square plus 2En times E square by 4 pi epsilon naught times 1 over R, expectation value of 1 over R, plus E square by 4 pi epsilon naught whole square times the expectation value of 1 over R square. These expectation values can be obtained from the hydrogen wave functions, and then these are given by this formula, equation number 8, where A is a Bohr radius. Simplifying the equation, we get E1R is equal to En square by 2mc square times 4n by L plus half minus 3. En is the unperturbed nth energy level of the electron. Next, we come to spin orbit effect. Electron having the property called spin implies that it has an intrinsic magnetic moment associated with it. Electron acts as a tiny magnet, in other words. The perturbation to the Hamiltonian comes from the interaction of this magnetic moment, the magnetic field of the nucleus in the electron rest frame. H is equal to minus mu dot B. Where mu is the dipole moment of the electron, and B is the magnetic field seen by the electron, produced by the motion of the proton. B can be written as mu naught I by 2R from our elementary theory of electrodynamics. Now I is equal to E over T, where T is the time period of motion. The orbital angular momentum of the electron in the rest frame of the nucleus is L is equal to RmB is equal to 2mr square 2 pi mr square by T. Velocity of light is given by C is equal to 1 over square root of mu naught epsilon naught. We can eliminate mu naught for epsilon naught. This gives B is equal to 1 over 4 pi epsilon naught times E square by mc square r cube times L. We need to write the magnetic dipole moment of the electron. Mu is equal to q times pi r square, q by t times pi r square, where q by t is the current. Recall that the magnetic moment of a loop is given by I times area. So the above expression corresponds to this I times area. The angular momentum is given by moment of inertia times angular velocity. Moment of inertia is mr square and angular velocity is 2 pi by t. So we get S as 2 pi mr square by t. From this, we get, combine these two equations, we get mu is equal to q by 2m times S. Q by 2m times S. For electron, charge is minus C, so it is minus E over m times S. There is a correction due to the fact that the electron resistance is not an inertial plane. It is accelerating. This correction is a factor of half. Including this factor of half, uh, the spin orbit interaction Hamiltonian becomes H prime S so is equal to E square by 8 pi epsilon naught times 1 over m square C square R cube times S dot. We need to express now we come to the calculation of this S dot L. We need to express S dot L in terms of L square, S square, and G square. We know that J is the total quantum number, total angular momentum. J is equal to L plus S. Squaring J, we get J square is equal to L square plus S square plus 2L dot S. Now, J square is equal to H bar square times J plus 1. L square is equal to H bar square times L plus 1. And S square is equal to H bar square S times S plus 1. S equal to half. So S square is H bar square times 3 by 4. Substituting this in the above equation, also the value of 1 over R cube, the expectation value, we get E so is given by E square by 8 by epsilon naught times 1 over m square C square times H bar square by 2 times J plus 1 minus L times L plus 1 minus 3 by 4 divided by L times L plus half times L plus 1 times n cube E cube. The total value of fine structure correction is given by adding the contribution of H prime R and H prime L. This is given by the simple expression E1 F fine structure is equal to En square by 2mc square times 3 minus 4n by j plus 4. The total correction, now including this with the unperturbed energy levels, we get the total energy Enj is equal to minus 13.6 electron volt divided by n square times 1 plus alpha square times n square divided by n square times n plus n by j plus half minus 3 by 4. And we describe this in this picture. Here the energy levels are shown. So for principal quantum number is n. For principal quantum number is n equal to 2. The orbital angular momentum can be either 0 or 1 or 2. The total angular momentum should vary from 2 plus half to 2 minus half, which is 5 by 2 to 1 by 2. So the energy levels are split according to not according to the values of L, but according to the values of J. So there are three distinct energy levels, and the relationship is shown in the figure. Similarly, for L equal to 1 state, J equal to 3 by 2, L equal to 0, J equal to half. So this energy level is shown in this figure. Thank you.